So this section is section 9.1, sequences and their limits. And you did a little bit with sequences, probably in pre-calc or maybe in algebra 2. So the essential question for this section is what strategies are used to find terms in a sequence and the limit of a sequence. So if we look at the definition of a sequence here, a sequence is basically a function. The domain is the set of positive integers. So in other words, you've got x values and they're positive. So we use the x values along the x-axis that are starting at 1 and getting bigger. Typically when we write a sequence, like right here, instead of using x, we use n, and that's an indication of the term number. So for this example here, it says find the first 6 terms of this sequence. So the sequence is a list of numbers, and we're going to start by putting 1 in for n. So we're going to go ahead and substitute in when n is equal to 1, we've got term a1, which is 3 plus negative 1 to the first power. So calculating that, that's 3 plus negative 1, which is going to be 2. So the a1 term, or the first term in the sequence, is 2. And so we can show this graphically and using our coordinate plane. So this is our first term, and its value is 2. We're going to go ahead and stick in a value of 2. So for the second term, sticking that into the expression for the sequence, 3 plus negative 1 squared, it's going to be 4. So our second term's value is 4. So if you notice, we can read these right off the coordinate plane, just like we'd read points in a function. So we'll put in a value of 3 for the third term. When we calculate this, we get a value of 2 again. And so we can keep calculating this. When n is 4, the fourth term of the sequence is 4. So we notice that the sequence oscillates between 2 and 4 depending upon what term we're talking about. And then we'll see the oscillation for term 5 go back to 2. And then term 6, it goes back to 4. So if we look at this, we can describe this series as a function by just replacing the n with an x. So 3 plus negative 1 to the x power. And we would say that this sequence diverges, and it diverges because of the oscillation. In other words, as we get to higher and higher terms in the sequence, they're either at 2 or at 4, but they never really trend toward one specific value. If we look at this example here, we want to write an expression for the nth term of the sequence. So in other words, we want to basically find the value, the expression for the function. So we have to start looking at patterns here. In other words, what do we have to do to get what do we have to do 2, 3 to get to 7? And so when we talk about these sequences, we talk about finding patterns using addition, subtraction, multiplication, or division, or maybe possibly square rooting something or taking something to a power. So if we look at these patterns here, and we can even talk about if we would see even patterns, we'd have twice the term. If we wanted odd patterns, we could subtract or add 1. That's a typo. It should be a plus 1. So if we look at this pattern here, we're just going to try something simple like adding and see if the pattern repeats itself. So 3 plus 4 is 7. If we repeat that pattern and add 4 again, we get 11. If we repeat that pattern and add 4 again, we get 15. So that must be the pattern, is successively adding 4. So we call that a recursive sequence. When we take a look at the terms before it to get the next term, basically. And so we have to start writing an expression for this nth term based on the pattern we see. So we know the first term is 3. So this expression is going to be the first term plus some sort of expression that we're going to use to get to any term in the sequence. And it's usually related to this rule we see here. In this case, it's a recursive pattern. Called it a rule. So for the first term, we know the first term is 3. It's just whatever is listed first. But we could also relate it using 4 by saying, well, it's really 3 plus 4 times 0. And that helps us see a pattern, because now for the next term, a2, we could call that 3 plus 4 times 1. And so you see I'm trying to incorporate this pattern that we see in the terms so that we can kind of generalize that pattern for any term, but relate it back to the first term. So the third term is 3 plus 4 times 2, and the fourth term is 3 plus 4 times 3. So to generalize this, we can say, well, for any term n, so this is the fourth term, maybe we want the 200th term, we're going to take 3 plus 4 times n minus 1. So if you notice, this n term is 4, or this n value is 4, and this multiplier is 3, which is 1 less. So that generalization allows us to see that pattern then to come up with the nth term. A sub n is our nth term, and it's 3 plus 4 times n minus 1. And so that general term, that general expression, then using that, we can get any term in the sequence. So in other words, if I want the 126th term, instead of adding 4 125 times, I can just mathematically use an expression 3 plus 4 times 126 minus 1, that's a typo right there, and that is 503. We can also simplify this expression up here to get an equivalent expression. So if I go ahead and distribute the 4, we get 3 plus 4 and minus 4. Then I can combine my 3 and my negative 4, and I can get 4 and minus 1. So if we think of the n as the x in a function, then the a sub n becomes the f of x. So if we look at this expression here, and going back to graphing, if we just call this x, then this would be our function value f of x. And that kind of gets us then to how we evaluate sequences and their limits. So we talk about this idea of convergence and this idea of divergence of a sequence, and that can be compared to then some function value. If we have a sequence that converges, then we have the function value that goes to some finite value. For divergence, we'd have a function value that goes to infinity. So if we can find the function value, then we can see if we have convergence or divergence after we go out infinitely many terms. So we then, if we think about that, we have a sequence that's a limit then. If it has a limit, then it's said to converge. So if you think about that, listing out a sequence to the infinite term. In other words, if we take this sequence here as the number of terms n goes to infinity, if we converge to a finite value L, then that's just a finite number, then that sequence converges. So rewriting the sequence, instead of calling it a sub n, calling it f of x, allows us to use kind of the strategies we've used before in determining whether or not functions have a limit as we go to infinity. And so it becomes just really evaluating the limit of a function. So we're going to look for this convergence of sequences with respect to thinking of these sequences as nothing more than functions. So we're going to let f be a function of a real variable. In other words, we're going to swap out the n and put in an f of x, and we're going to find out if it has some finite limit. So when we talk about then finding these finite limits of these sequences, then what we basically say is if we can find the limit of that function, then the limit of the sequence itself must be that same value. And then we can go back to our properties of limits. And we have our basic properties. We have our additive property, our multiplicative property, multiplying by a constant property, and a ratio property. So the same way we deal with numbers, we can deal with these limits of these sequences. So let's take a look at this first sequence here. It says determine the convergence or divergence of this sequence. Find the limit if it's convergent. And really, it's kind of written, I almost kind of think of it's written backwards. If we can find the limit, then we know it converges. If the limit is infinite, then we know it diverges. So really, it comes down to finding the limit. So we're going to go ahead and take the limit, and I left it in terms of n, or we could put it in terms of x. It's really kind of splitting hairs, but I'm going to find the limit of this as n goes to infinity. I'm going to check for indeterminate forms. So in other words, if I just plug in infinity, then I get infinity over infinity, which is an indeterminate form. So I'm going to go ahead and use L'Hopital's to simplify this. So derivative of the top is 1, derivative of the bottom is 2. So the limit as n goes to infinity of a half is just a half. So we say that this sequence then converges to a finite value of a half. So if we would graph this sequence like a function, so when n is equal to 1, then we have 2 over 2, which is 1. So that's this point right here. When n is equal to 2, if we had 3 over 4, which is 3/4, which is right here. When n is equal to 3, if we would have 4 over 6, which is 2/3, which is right here, we can see that those finite terms will start to trend toward the value of a half. So we say that the limit of this sequence is a half. In other words, all of these values trend towards a half as we go out to the infinite term. If we look at this example, this example has some factorials in it. And so the first thing we need to do is simplify this to get this into a form where we can evaluate its limit using the strategies we have, simplifying algebraically, L'Hopital's, things like that. So we have to look, if you remember what the factorial sign means, or what the factorial sign is, right? That factorial symbol is it just means successive multiplications. So if we look at 4 factorial, it's 4 times 3 times 2 times 1. And so if we can re-express ratios. If we simplify these expressions, we can think of this as 3 factorial over 5 factorial. So the top then would be 3 times 2 times 1. The bottom would be 5 times 4 times 3 times 2 times 1. We have some canceling going on that we could do. And then we're left with 1 over 5 times 4. So we can do the same thing if we re-express this as well. So looking at n minus 2 factorial over n factorial, we can re-express n minus 2 if we think about this. 3 factorial is 3 times 1 less than 3 times 1 less than that. So if I set up the top here, then n minus 2 factorial must be n minus 2 times n minus 3 times n minus 4 times dot, 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 and so on and so forth. And n factorial is going to have to be n times n minus 1 times n minus 2 times n minus 3, and it kind of goes on and on as well. Well, if you notice, after this term, the n minus 2 term, things start canceling. This n minus 3 is going to cancel with this n minus 3, this n minus 2 is going to cancel with this n minus 2, this n minus 4 would cancel with this n minus 4 if I wrote it out far enough. So we're left then with 1 over n times n minus 1. So that's the simplified expression for this sequence right here. So we could evaluate the limit of this, and it would be the same as evaluating the limit of that. So we're going to go ahead and evaluate this limit. We can go ahead and stick infinity down here. It's not indeterminate. We get 1 over infinity, which is 0. So the limit of this sequence then is 0. So if what we say then is that this sequence converges, and it converges to a finite value of 0. So if we thought of this as a function and we graphed it, it would look like this. As we stick in a value of, we'd have to start this at 2, because 1 would be asymptotic, but this would be 1 over 2, which is a half. And then if we put in 3, it would be 1 over 6. And if we put in 4, it would be 1 over 12. And so on and so forth. So these terms, as we go out infinitely many terms, these terms tend to go to a value of 0. And so that's what the limit is of this sequence. Here's another sequence, 7n over n plus 5. And let's go ahead and take its limit to see if it converges or diverges. So I'm going to go ahead and set up the limit as we take out our terms to infinitely many terms. I do a quick check to see if I have an indeterminate form, and I do. So I know I need L'Hopital's, so I go ahead and take the derivative of the top and the derivative of the bottom, and I get 7/2. So this sequence then converges to a finite value of 7/2. So looking at this sequence, if you notice, this sequence starts low and comes up high. So as we, this is going out 5 terms, this is going out 10 terms, this is going out 15 terms. So if I would put a 5 here, it would be 35 over 15, 35 over 15. It would be the value of that 5th term, and so on and so forth. So going out 55 terms, you can see this is getting closer and closer and closer to a value of 7/2 or 3.5. So as we go out infinitely many terms, then this the shape of this function will be really close to 3.5. Or we could just say 3.5 is that. If it's the limit, it must be that asymptote that it approaches. And that comes in handy when we talk about the next two concepts. Noticing that whether or not it approaches its limit from below or above, and what that limit is. And we'll get to that in a few minutes. I want to do a quick review of the squeeze theorem from last year. It has to do with taking limits, and we can look at this as a sequence as well. And not this sequence in particular, sine of n over n, but what we compare it to is going to be a kind of a really important expression as we go through this chapter. But we know that the value of the sine function fluctuates between 1 and -1. And since sine has that oscillation, we can't use that to determine convergence, kind of like at the beginning of this video when I was listing the terms 3 plus -1 to the n, and it was just oscillating between 2 and 4. Sine does the same thing; it just oscillates. So if we want, since this sequence oscillates between since sine oscillates between -1 and 1, we kind of have this alternating sine pattern going on. So we take a look at the maximum value of the sine of x, and we know its maximum value is +1, and the minimum value is -1. So instead of writing sine x in the numerator, we're going to replace that numerator with 1 and -1 and look at those two as sequences. So instead of sine, and I replaced it with an x because n kind of gets a little tricky when you have the word sine in front of it, which has an n. So instead of sine, I put just 1. So this is kind of a maximum, the biggest that this sequence would be. So it's 1 over x, or 1 over n. And we know the limit as x approaches infinity. If we put infinity down here, we get 0. And so there is 1 over x. If we notice, it kind of hits all those peaks of the oscillations. And we know that as we go out to the infinite term, way out at infinitely many terms, this is going to approach 0. And if we put -1 at the top and take the limit as x goes to infinity, well, -1 over x looks like this. And so if we go out infinitely many terms, which is the same as putting infinity down here, we're also going to approach 0. And so we know that we can make a conclusion here, because since the sine of n lies between these two values, then this is always going to be between these two numerically. So, and you can kind of see that, you can definitely see that on the graph here. As it oscillates back and forth, it oscillates between these two boundaries, so to speak. So when we take the limit then, as we go out infinitely many terms, we can say that sine of x over x, that limit is 0, based upon the fact that these two both go to that same number. And just kind of as a side note, we have this absolute value theorem that says if we have a sequence and the absolute value of that sequence is 0, then the actual sequence, the limit of the actual sequence is 0. In other words, if we make all the terms positive, then even if they oscillate from positive to negative and positive to negative, they're still going to go towards 0. That's kind of what that's saying. And so now we're kind of setting up this idea of boundaries here. And that's going to take us into these last two definitions. One's called monotonic, and the other one's called bounded. So monotonic basically means that you have a sequence, and that sequence is moving in one direction only. In other words, it's either not decreasing or it's not increasing. So again, we can think of the sequence as just a function, and that non-decreasing characteristic basically means that, well, if it's not getting smaller, it's either staying the same, which means with all the equal signs, or it's getting bigger, right? So this term is bigger than that term, this term is bigger than that term, and so on and so forth. So you start out little, and you get bigger and bigger and bigger and bigger. And non-increasing then is just reversing that. You start out big, and you get smaller and smaller and smaller, or you stay the same. So, so in other words, you're not doing that oscillation up and down. And so if we think about that, non-decreasing basically means something that looks like this. And non-increasing means something that looks like this. So if we look at those, they all have a derivative that doesn't change sign. In other words, if non-decreasing would look like this, then we would always have a positive derivative. Non-increasing looks like this, we'd always have a negative derivative. So we can check the derivative and determine whether the sequence is monotonic or not. As far as a bounded sequence goes, we've been doing that actually all along by determining whether or not there's a limit. So if it approaches the limit from underneath, then we call that having an upper bound. In other words, it's coming down from down low, and it's approaching that upper limit, and that's the biggest value. And if it has a lower bound, that means the terms values are starting out high and decreasing, and approaching a bound that's at the bottom of it. And just that last squeeze theorem had a bound on the top and on the bottom. So the bounded sequence, we've really been checking for that all along. That's determining whether or not the limit exists. So, so we have that upper bound and that lower bound. So another term for these bounds then, they call them M and N. Basically, they're just horizontal asymptotes. So for instance, if we look back at the sequences we already talked about, here's 1 plus n over 2n. We know that this sequence has a limit of 1/2. So that limit 1/2 is its lower bound. 1/2 is right here. It's beneath the entire sequence. So so that we would say that this sequence has a lower bound of 1/2. Let's take a look at one of the other sequences. Here's the sequence with the factorials. We saw that that went to 0. So that's also a lower bound because the sequence's values are all greater than 0. So if we go out infinitely many terms, then the value 0 ends up being a lower bound as well. If we look at, oh yeah, this is the 7n over 2n plus 5 sequence. So that limit was 3.5. So if you notice, the terms of this sequence are all smaller than 3.5. So 3.5 must be an upper bound of that sequence. And likewise, you can see that, and I should have, maybe I can go back, there I can go back. If we go back to these, we can talk about monotonic too. If we talk about the monotonic nature, we see all the slopes here are negative. So if I took the derivative of this, and then I could show that that derivative always was a negative number. And if that derivative is always a negative number, then that must be non-increasing. Likewise, if I go back to this one, notice these derivatives are all positive. And you know, the tangent lines are all positive slopes. And so then this must be non-decreasing. And so if I took the derivative of this expression, I should be able to prove that that derivative would always be positive. So that's how we would show that that this, in fact, is monotonic, non-decreasing. Let's go through an example in terms of these, in terms of monotonic and bounded sequences. So we have this sequence. We have to determine if it's monotonic, and then we were to talk about the boundedness. So in order to talk about being monotonic, we're going to look for the derivative that doesn't change and make sure that derivative doesn't change sign. For boundedness, we're going to find the limit. So let's talk about monotonic first. Let's think of this as a function, 3x over x plus 2. We need to take the derivative of this. So we're going to use the quotient rule. So remember, quotient rule is low d high minus high d low. So low d high is going to be x plus 2 times the derivative of 3x, which is 3, minus high d low, so 3x times 1, all over low squared. And so I'm going to simplify the top here. Looks like I have 3x plus 6 minus 3x. So 3x plus 6 minus 3x all over x plus 2 squared. I'm not going to touch that. I'm going to simplify the top a little bit more though, because I have things that cancel, so the top it just ends up being 6. So 6 over x plus 2. So when we talk about monotonic now, we have to look at this and say, is it always positive? Is it always negative? Or does it switch? Is it equal to 0? Does it switch signs ever? And it doesn't, right? If it were equal to 0, we'd be able to make a top 0, and we can't. So we can say that this is always positive. We know x is always positive because that's the definition of a sequence, is it starts at 1 and is positive, the domain's positive integers. So this is always going to be positive. 6 is always going to be positive. So this derivative is always positive. So it's monotonic. And if the derivative is always positive, it's increasing. So this is actually, I should actually call this non-decreasing. So this is monotonic non-decreasing, or you can say monotonic increasing as well. Let's look at the boundedness. The boundedness, we're going to see if it has a limit. So we're going to go ahead and take the limit as n goes to infinity, or as x goes to infinity. I kept it in its function form. A quick check, if I put infinity in the top and bottom, I have an indeterminate form, infinity over infinity. So I'm going to go ahead and differentiate the top and differentiate the bottom using L'Hopital's. So I have 3 for the limit. So this is bounded. It's got an upper bound of 3. And so we know that it's monotonic and bounded based on those two tests. So we have this final theorem that says if a sequence is bounded and monotonic, then it converges. So this must converge, and it converges to a value of 3. So our essential question, the strategies used to find terms in a sequence and the limit of a sequence. Sequences, just to remind everybody, are just another technique of writing functions. Limits are defined by the presence of horizontal asymptotes. And that gives us our bounded behavior as well. So you can go ahead and, this is wrong, you should be working on section 9.1, sequences web assign.